So as my title suggests, that I will talk about magnetoplasma dynamics today, and basically it's a theoretical talk with some experimental validation. I will show at a later phase. So first of all, what is plasma? So as we go in our nature, so we will have mostly three states of matter, starting from solids, and then if you increase its temperature, so the random kinetic energies will be increased, and then once the molecular forces will be weak, and then it goes to the liquid phase, it will increase more the temperature, and then it goes to the gaseous phase. And then if you increase the temperature even more, so then atoms, the electrons will be here, and it will go beyond the atom, and eventually we will have charged particles like electrons and then ions, and even we could have some neutral atoms also. So then it is a state of matter in which we term it as plasma. So if we go to this degree of ionization, that how much ionization should be there to term a state of matter as plasma. So as you can see from this ionization equation, this Ni by Nn, where Ni is the number density of ions and then Nn is the number density of neutral atoms. You can see this is famous ionization equation which says that at certain temperature at certain temperature this should be the number ratio or number density ratio. So for example, we know that at room temperature we don't have plasma, right? So within this room we will have air, and that is certainly not plasma. But if we want to validate our ionization equation with that, we can consider that okay, air will have around 78 to 80% of nitrogen. So if we consider that nitrogen will have ionization potential of 14.5 microvolt, so we will see that Ni by Nn will be very less than 1. Which means again, as we expect that air is not a plasma, rather this is just a gas. But if we go to different plasma systems in our in nature, so one is the man-made plasma, that is Tokamak machine. As you see in this figure, this is a like donut state magnetic field confinement in which plasma could be confined. So in that Tokamak machine, we will have certain number density, temperature, and for that we will have Ni by Nn is very much greater than 1. Suggests that this is certainly in the plasma state of matter. But then if we go to another plasma system which is very larger in length scale, so while I am talking about tokamak, so it's very smaller kind of thing which is man-made in our laboratory, which will have a dimension of let's say 100 by 100 centimeter. But then if we go to solar corona, which is the outer atmosphere of sun, that is again a plasma system. So how do we define solar corona? Is the outer atmosphere of the sun, but then we don't see this atmosphere at the by the naked eye when we don't have solar eclipse. But if we have solar eclipse, the more dense and more intense disk is occulted, so then we could see this ray-like structures in the outer periphery of that. So that's the coronal structures. Why we can't see when there is no solar eclipse? Because it has low density in comparison to the different structures what we have in the disk. So once we have that low density structure is only emitting, so then only we can see those structures. So in the Soho equation is there underlying results for yes. So such are yes. So here I think this is only for high temperature and high density plasma only. Since I am talking about plasmas only, so therefore I can use it, but it is not usable for all kind of gas. So for solar corona also you would find that Ni by Nn is very much higher. So it tells that for plasma we will have very high ionization ratio, but is it all about plasma? So that's not. So a plasma is basically quasi-neutral gas of charged and neutral particles which exhibits collective field. Now what does it mean by quasi-neutral gas? So in plasma we have both ions and electrons in large number of ions and electrons. So a plasma is such that in which the total amount of positive charge and total amount of negative charge should counterbalance each other. Such that there will be a quasi-neutrality, that means it is a neutral gas at a certain layer scale. Okay. So other thing is collective behavior. What does it mean by collective behavior? So when we have charged particles, so what happens is those are moving, right? So then it could generate magnetic fields, and then if we have charged particle, it could generate electric fields also. And then eventually there could be collisions between those charged particles also, because those are moving random. So these are different kind of interactions they could have. Now collective behavior means that if you have only a gas, so molecules can only interact with each other by some collisions, but there will be no long range interaction between them by some forces, right? Now if we have plasma, we have charged particles, so due to this electric and magnetic field, they could have a long range interaction among themselves due to the electric and magnetic field of the other particle. So that's why for one charged particle, it will generate some magnetic field, and within that magnetic field, all the other particles will be collectively moved. So that's the collective behavior. So that's
what is the range like long
range. Yeah. So long range is let's say it would go from, let's say in this case, so it's in centimeter, but for this one it would be go to megameter, 10 to the power 6 meter. So it depends on how much number density, temperature, those things.
So within the plasma there is some spherical region in which only
yes. So that's why the quasi-neutrality holds for higher length scales. How much higher? I will talk about that. So if you go for quasi-neutrality and collective behavior, what happens is, let's say we consider that it is in quasi-neutral state, but then let's say you put a charged particle which is, let's say, negative or positive. So once you put a charged particle which just breaks the quasi-neutrality, what happens is it will generate an electric field, right? So initially you have no like charge imbalance, you have the same number of positive charge and number of negative charge, but then you are putting an extra charge on. So due to that extra charge, it will generate electric field, right? So if you don't have any kind of other charge particle, if you have only that particle only, so that would have a Coulomb potential, right? Like Q is the charge, so 1 by R would be this Coulomb potential will go over this orange line as we move from the charge. But then if we have more number of charge particles around that particular charge particle, it will shield that effect of the charge that for which the charging balance is. So therefore, it tells that if we have a length scale which is higher than the lambda d. Okay. So how does lambda d is defined? Is this lambda d is like root over epsilon kT by d square. But for different plasma system, we will have different values of number density and temperature. Depending on that, you will have values for lambda d. Okay. For example, tokamak and solar thermal, you will have this number. So if we are going a length scale in which we are trying to study the dynamics, which is higher than this length scale at this particular plasma system, so it tells that it is in quasi-neutral scale. Okay. If it is less than that, we are not going to consider the plasma system. But for simplicity and actually in the nature, we have systems at which the dynamics is happening at very much higher length scale than this. And also within that device sphere or device length, like if we consider this to a radius, like this lambda d, let's say you have a charged particle, so we are going far away from that. If we go from up to lambda d, that is the device sphere, we consider 3D volume. Within that 3D volume, we will have higher number of charged particles. That is another approximation of plasma. Okay, so the idea is you have a plasma column. So if you have a charged particle which is creating charge imbalance, so then the potential into that would be only filled within this sphere. So if you, let's say, if you are saying that this is my entire zone in which the dynamics is happening, so in comparison to that, this sphere is very much smaller. So then within that you will have a quasi-neutral. Okay. So okay, now we have charged particles, then we have magnetic fields also. Now this magnetic field and electric field will have two components. One is due to the charged particle itself. Because charged particles are there, that will create electric field, but that electric field will be only filled within the device field. If we are going higher dimension, so we will not see that. But magnetic fields will not be shielded. So therefore magnetic field will be there due to the motion of charged particles itself. But then the other thing is we have to have external magnetic fields to confine plasma. So this magnet B is having contribution from both internal motions and the externally given magnetic field. Okay. So now if we go for this equation of motion, so it is that if you have single charge particle, for example electron or ion, if it is going in a motion in a external like total magnetic field with a velocity v, so that would gyrate around the magnetic field with a certain frequency, certain radius. Okay. So as the mass r basically depends on like mass of the charge particles. So since ions will have higher mass than electrons, so then for ions that will have higher radius, as you can see from the figure. And for tokamak and solar corona, you can see like parameters like Ri will be 5 millimeters for tokamak, but while in solar corona it will be 1.4 millimeters. Okay. But then the problem is this is for a single particle, right? But then in plasma we have many particles like 10 to the power 18, 10 to the power 20 particles. For that, this much particle you can't solve, but this is very much cumbersome to solve each individual particle's situation. So then we need to go for statistical approach, in which we define like distribution function, which tells that if it is a function of r, then position and then velocity and as well as time. So then it tells that at particular position, let's say r and r plus dr, if the particles will have velocity around v and v plus dv, so then the distribution function gives us the probability of finding the particle at that particular space in 6-dimensional space for a single particle, but if we have n number of particles, so the space will be 6 dimensional. So that's your F alpha, and then F alpha is basically alpha the species. Species means either it is ion or electron. So now if we have Grashof equation which tells that how the distribution function is going to change with time. Okay. So as you can see from Grashof equation we don't have any term on the right hand side. So there is 0. So df alpha dt is 0. That means your distribution function is not going to change with time. It is like a conserved quantity. Okay. Why? Like when we should consider such conservation, that is only if we don't consider or we don't have short range collisions. So as I said, that there will be short range collisions, that is the short range interaction, and then there will be long range interactions, that is only because of electric and magnetic fields, right? And then we are not considering electric fields. So we could have this equation. What we do, we just do some mathematics that if alpha is a function of r, b and t, we take the derivative of it and then we could find out this terms, and then in place of dv dt, just replace this by the previous equation like m dv after dt, so that is q by n plus v. Okay. So now if we consider that along with the long range interactions, we would have the short range collisions also in between the particles. So then we would have a term on the right hand side, and then the equation is termed as Boltzmann equation. Okay. So this equation shows how the distribution function is going to change while it is subjected to motions of the particles, which in turn generates magnetic fields. Okay. Now, what if we are in a time scale which is higher than the relaxation time of ions and electrons? So there are collisions. So then those collisions, in between two subsequent collisions, you will have a relaxation time of each electron, right? So more and more frequent collisions will have lesser relaxation time of ions and electrons. So if you are in a time scale, for example, let's say you have collisions which are happening, let's say at 1 and then the next collision is at 0 seconds. So you will have a relaxation time of let's say 10 seconds. But then if you have a dynamics which is happening at let's say 100 seconds, let's say after 100 seconds only that things are changing in a certain system. So in that case, you can consider to go to microscopic to macroscopic scales, because while your dynamics is very much slow, so what happens is within that you have frequent collisions, they will generate a thermal equilibrium, but then that thermal equilibrium will be different for electrons and ions initially. Why? Because if you are at less scale now, for example, I just showed in the previous slide that these are the peripheries in which ions or electrons are moving, right? So now, let's say this is your radius of ions and this is your radius of electrons. Now if you see, this is is your system. You are very close to see that electrons or ions are moving differently. But if you have a length scale which is much higher than this, so then we can't distinguish the motions of the electrons and ions. But right now, while I am doing the statistical approach and doing the microscopic averaging initially, I am in a length scale which is in this case. So we would have multiple collisions, but we are in a length scale in which we can distinguish the motions of electrons and ions differently. Okay. So yeah. So in that case, we could do the microscopic averaging over the velocity space of the distribution function. Now, for example, while doing the microscopic averaging, this is just a general formula that if we have certain variable, there is a g, which is a function of r, p, and t, and then I am making the average in that velocity space, and then have a microscopic average quantity, which is macroscopic one, this is g, r. Okay. So, for example, very specific examples are this chain alpha RT. So, this is just density of charged particles. So, how does we reduce it? It's just integration over the velocity space over the distribution function.
The shortening potential is less than the divided length that you were talking about.
No. This is higher. Like divided is the first thing. That we have every dynamics is happening at a higher length scale than this. Then only we are considering it plasma. So in alpha RT gives you the number density for, let's say, alpha can be electron or ion. So this is the number density of electrons and ions. How do we get it? We just integrate over the full velocity space, and then we would have only information of the number density at certain positions at a certain time. What we want. So this is a macroscopic quantity, and then U alpha RT is the microscopically averaged macroscopic velocity. Okay. So here we have V, which is the microscopic velocity that we have for charged particles, and then we just do the multiplication with F alpha and then integrate it over V3V and divide it with the number density. It gives us the velocity in unit volume. So using this n alpha and u alpha, you can go to calculate this tau and j. So this is charge density, this is current density. So once we have this this average quantity, we could go to calculate tau and j. Okay. So now what we can do with tau and j? So if we have these three sets of equation on the left hand side, first of all we have Boltzmann equation, which tells with time how the distribution function is changing. But then you need to prescribe how E and B these are changing, right? Because that's only give you the closure. You know these things, but if you don't know how with time E and B is going to change, so you are not getting a closure to this equation.
Usually, the right hand side, the horizon term, you locate that as partial derivative of the with respect to time.
So this has different kind of specific.
This is related to the interaction of the particles.
So that actually changes the distribution function of that. If it is not there, it will conserve analysis.
Right hand side is 0, that means there is no collision.
So partial derivative on the left side.
Del F alpha del B. So that's the entire thing. Like how it is changing only with time. So that's not total derivative. That is only the derivative with time. And then this is only, this will be only there if we have constant collision. So if we don't have, we will have 0. So we have this equation, and then we have this average quantity, and then we have finally the Maxwell's equation. So in the Maxwell's equation, you can see that del dot E, that is tau by epsilon naught. In case of plasma, tau should be almost equals to 0 because we are considering perceptibility, and therefore we are not considering electric field also. Okay. But in principle, how we are calculating tau from this microscopic averaging, and then that tau can be in principle put in the del dot E term, that will give you an electric field, how it is going to change. And then curl of E is minus del U del T, so that's the Faraday's law. So that is how your magnetic field is going to change, and that would generate an electric field in principle, which is a secondary quantity. Okay. And curl of V will be mu naught J plus 1 by c square daily del T, while this 1 by c square daily del T will be not considered in our system. Why? Because if you go for dimension analysis for this, so it will only be there if we have a dynamics which is happening at relativistic case. We are considering non-relativistic dynamics. For this, the displacement current term will not be here. So you will be taking this to 0 on the right. Curl of B will be only mu naught 0. And then the divergence of D is 0 is just magnetic monopole divergence. So using all three sets of equations, we will be ending on this equation of three equations. So this is like a 4-5 page of calculation. You can see this del in alpha del T plus divergence of something in alpha equal plus. It tells that how your charge is going to be conserved, right? So that's just mass continuity of charge.
So from the first slide, whatever you discuss, assuming classical. So here, your displacement current will not be there. Only after that you can consider relativistic. So in the example of proper line, the temperature was around 10⁸. So at that high temperature, particles
That will be in the classical level.
that is also interesting.
You have to have 4 to 4 more acceleration of that particle. 4 to 4 that's what relativity. So then we will have this set of equations. This is charge continuity, and then this is the momentum equation, where R alpha is the tension term coming from this consideration of short range collision. So this has some certain specific expression like Q alpha in alpha eta J by J is correct. And then here you will have a Q alpha. So you can see that if you are not considering the short range collision, this R alpha and gamma minus 1 Q alpha will not be there. That's only some derivative or something coming from the del alpha. Okay. So if you don't have that, you will have 0 on the right hand side. This is charge continuity, this is momentum equation, and this is the pressure balance or pressure energy density, how it is going to change. So now here you can see still we will have alpha in suffix of this equation, which tells us that these equations will be for electrons as well as ions. We are in a fluid state in which we have frequent conditions. We will have different fluid for ions and electrons, but still we are in a length scale in which we can distinguish the motion and the fluid properties of those ions and electrons separately. We are not in a length scale in which we could not distinguish the fluid properties differently. So now we have these equations, and then if we consider that, again as I said, that if we consider this is my length scale over which some dynamics is happening, we are not going to distinguish this one. Then only this sets of equation on the left hand side, if we consider that let's say Ne is the electrons number density multiplied by Ne is mass of the electrons plus charge density of ions and then multiplied by mass of ions. So that gives you rho, and this rho is your plasma density. We don't have any information about electrons and ions separately. Okay.
Here this rho is also function of position.
Yes. Rho is function of position as well as that. Because N, E and Ni both are changing in like at certain position.
So this N alpha is N E and N I.
Yes. N alpha will have to form N and so these three sets of equations, like three equations, we have 6 equations. But here since you have then Q alpha and U is like a vector, so for example if you consider only electron, so what happens is first equation is your scalar equation like del in alpha, so that one, Second equation is a vector equation that will have three components if you are going to three dimension. Third equation is again scalar equation, right? So for electrons you will have eventually 5 equations. For ions you will have a hierarchical in which we are not distinguishing electrons and ions differently. So then we are taking this set of equation in which
They are not independent.
so now you have rho, which is total plasma bulk density instead of differently describing ions and electrons. Similarly for tau, so this will be 0 because we are considering Gaussian equality. D will be the plasma velocity, and that will be given we have this expression J and D are subsequently. So with this much consideration, we will end up with this equation.
This is small p is momentum. Small p is equal to
This one, this is thermal pressure. So momentum is like rho v. Actually, it is momentum density because we are in a volume, right? Plasma is a volume. So everything is in terms of density. We are not considering mass. We are giving mass density. Similarly, we are not considering momentum. We are giving momentum. Okay. So eventually, we end up at this set of equation again. Now this is magnetohydrodynamic equation, which is single fluid equation. We don't have any consideration of electrons and ions differently. We have plasma, which has density of rho, which is the velocity of v. So this tells us how mass should be conserved, right? Second equation is again momentum equation, momentum density, how it is going to conserve. Now if you remember, in fluid dynamics we will have a Euler equation, in which again we will have a rho g term if we consider gravity, but for the time being we are not considering the gravity. Okay, but now in this equation we have an extra term which is J plus 2. That is not there if we don't have magnetic field, because if we are considering only fluid hydrodynamic case, we don't have this term. I will discuss about the role of J plus 2 later on. This additional term in our case is magnetohydrodynamics. Okay, this is your pressure equation, or let's say energy density equation, and this is again del V del V plus this third equation, where E is defined as E should be minus V cross V plus eta J. Okay, so and divergence of E is 0. So this is the set of equations we have finally with this kind of approximations of, let's say, consideration. Okay, so
the second equation here, P is vector.
here,
Yes.
yeah.
So the dot product is in between B and
This one.
B and
So
gradient of your
here, so this is a V dot del that operates on V. So V dot del will give you a scalar quantity, and that will operate on the vector of the
I have a question on this development of this equation. This is where electron and plasma look like they are decoupled. That is why very nicely comes.
Here this is electrons and ions.
Yeah.
Both
They are
decoupled.
independent. So what is the reason physically that they are decoupled?
Decoupling is, I mean, by decoupling what it tells is, like, if we go to a lens here in which we see that okay, ions are moving in a certain trajectory, electrons are moving in a certain trajectory.
This is on the some mesoscopic scale where you cannot see it.
But if we are going for high lens scale, so we will not see the trajectory.
Coupling, then you cannot come up with this nice measurement.
So finally we will end up with this equation. So okay, I have shown lots of equations. If we want to summarize what I learned, we start with kinetic theory, where we have distribution function, we have Gaussian equation and Boltzmann equation. Then we consider frequent collisions. So we have a time scale which is higher than the time scales of relaxation time. So then we will have two fluid theory, where we have different fluids for electrons and ions. And then we go to large scales where we could not distinguish these motions differently. So then we have single fluid theory. We are not considering electrons and ions. Everything is a single entity. Okay? So that's our magnetohydrodynamics. Now we have equations, but if you look at these equations, what they are? So those are partial differential equations which are coupled with each other. And in all of these equations, you have certain terms which are spatially changing which has dependence on the spatial dimensions also. So you have spatial derivative, you have temporal derivative. Okay. So how do we solve them? We could not solve them by pen and paper because those are different sets of equations and for coupled with each other. So then we go to the technicalities. If you go for diffusion equation, what does it tell? So that's just an example. So let's say you have certain quantity phi, which is changing with time, and then you have diffusion term on the right hand side, and eventually what computer does? So computer discretizes your space. Any domain, if computer is going to solve, so it will discretize. You will not consider it to be a continuous system. So it will have main points like A is like a spacing between 2 points in the spatial domain. So eventually this second order derivative of A2 by L2 that can be written in terms of this part while you are solving computational. And then eventually you have d phi dt. So that is the Euler equation that is that. So if you have a time step which is going with A, so if you know, let's say at t equal to 100 seconds you know something, and then you want to know that quantity at that particular location at t equal to 101 second. So that's your choice how you are going to do that. So it tells us that forward time centered space method FTC. Okay. Now if you go for a practical example in which this equation holds. So let's say if you have a steel container which contains hot water which has temperature of 50 degree, and then the steel container will have initial temperature of 20 degrees throughout, and then this entire thing is kept in a cold water system which is at 0 degree. So what happens? In this equation we have phi, which is a function of x and t. So spatial dependence, we have temporal dependence. Now here we have, if we want to see how the steel container is going to change its temperature distribution. Okay. So what diffusion equation does? If we have very high gradient of something, it will diffuse that gradient. Okay. So now we have so this 20 degree temperature, so that is the initial state for steel container. Okay. So that's the initial temperature of steel container, and then you have 50 degree hot water on the top side and 0 degree cold water on the bottom side. So you have two boundaries where is the values of temperature. Okay. So what happens is we want to know as time progresses how the distribution will change. For example, if we consider, let's say this is our system. We have two boundaries, right? For this, you have 50 degree temperature here, you have 0 degree temperature here, and then you have 20 degree temperature here. So very local to the boundary, we would have higher gradient of temperature because this is 50, this is 20. So you have a higher gradient of temperature. Similarly, at this is 0, this is 20. So you have higher gradient. So what diffusion equation does is it will destroy the gradient as we advance in that. So that is what we find. Like so at t equal to 0.01, you can see that this 0 is close to top boundary, this 100 is close to this bottom boundary. You can see close to boundary you will have higher gradient, and then eventually as we go for lesser t equal to at t equal to 10, we will see that everything is diffused. Okay, so that's what diffusion equation does. So from this slide, the focus is only on, let's say if we have temporal dependence, we are going to give an initial condition. If we have spatial dependence, we need to go for boundary conditions. In our equations also, we will have both, right? We have del rho del t and the divergence of something. So we need to specify both initial condition and boundary condition while we are solving those states of equation.
So how do you decide the magnitude of A? Like
Magnitude of
A. The term you
A. So it depends on how much accuracy you want. Let's say if you go for very lower A, you are basically going for the continuous system, right? So that's the accuracy goal. So okay, so this was our set of equations. Now I just write OG on the right hand side. these are the equations that we have previously. But then the problem is now. Okay. So let's say this is our simulation domain. So what happens is it will go for this block size discretization in the right and left hand side. Okay. So it will consider everything in each block. Let's say this is a square. If in 3 dimensions it's a cube or something like that. This is your entire simulation domain. What we do is this x plus a x minus a, those are the grid spacing. So these are the grid spacing. Let's say this point and this point. So we have a grid spacing of a. So what code want to do? So it will like solve for let's say density in between this particular mesh. How will you like rho will either increase with time or decrease with time. If we go for the first equation, it is in conservative form because within this, if rho del rho del t is let's say decreasing with time, eventually divergence of rho v that should be increasing, right? Greater than 0, which means that if we have a diverging flow, you have del rho del t is going to be decreasing with time, right? That's what we expect. So that is for conservation of mass. So code wants to have the conservation equation. Once it is trying to solve this. Okay. For the first one, we have that form, but for the other 3, we don't have that form, right? So what happens is, let's say you have anything, let's say del u del t, and then something divergence of some function of a u, which is equal to 0. If you don't have any non-conservative number, so what happens? How u is going to change? It depends on this divergence, correct? But if you don't have this form, so code will have very difficulty calculating how u is going to change, because it would not have any flux of something which is either coming in or going out. So if you don't give certain kind of properties which would either coming in or going out, it would not tell that how it is going to change the quantities within the cell, right? That's why we want to rewrite this equation in such a way where we will have a conservative form, where something is changing with time and the reason of that change is something either coming in or going out. Okay, that's only our focus. So if we go for like this would end up with certain kind of like again this is 4-5 page of calculations with some vector and tensor identity. We will end up with this. As you can see here, everything is in this del t plus something divergence of time. Okay. Now we have conservation equation. Here, this rho Pv is Reynolds stress tensor. Okay. And then this half v square I minus Bv is Maxwell's stress tensor. So these are tensorial quantities. And eventually, so these are the sets of equation we have in terms of conservative form. Okay. Now we have conservative forms of the equations. So then what would solve them?
The boundary condition will have to be specified for each mesh in this case.
No, boundary condition is specified only at this.
But it is being solved for one particular
Initially, if it like we will update, right? Later. It's up to you that at which time scale you are going to like save your data. But then before that, so there are two things. One is physical time, that's decided by you. But then there are iterations time, which is like decided by computer. Right? So we have this set of equation, and for this, what we have is we have 0 for ideal case. For that, we will have this equation in which we don't have any term on the right hand side if we are not considering that. Okay. But then if we have this j, eta j square, where eta is nothing but a resistivity or diffusivity, so we will end up with this system. Okay. So now we have some equations which code wants to solve. quantities are going to change with time. So you want to know how something flux or something is coming in or going on, right? So you want that conservative equations or conservation of something to see how the quantities are going to change. So that's, if we write it in terms of that, or we'll find it easier to solve the equation. It is always not necessary, but in most of the numerical techniques, this is how people solve the equation. Okay. You want to like reduce the difficulties. So that's how we solve. Even for this equation, you could see that in this equation you have something on the right hand side, right? So code will only solve that part as a source term. Okay, other terms will be solved in a different manner, and then eventually you will like kind of it. Okay, so that's easier for numerical techniques to solve the equation. That's why we need the conservative forms. Okay. So now we have some sets of equations. We want to know whether we can use the same set of equations for different plasma systems. What do we mean by different plasma systems? As I said that for tokamak, everything is in a centimeter scale, and every dynamics is happening in a microsecond or nanosecond time. But if we go to solar corona or astrophysical systems, that would have a very higher length. Let's say 10 to the 6 meter or something, and every dynamics is happening at a second or like 10 second or 100 second or so. So time scale and length scale, everything is different, density is different. So for different plasma system, we want to know if the other conditions are there, that it will follow the single fluid theory, magnetohydrodynamic theory, with the same set of equation will be used for different plasma systems. So then it takes the scaling, that we have to make dimensionless each of the quantities such that same set of equations can be used for tokamak as well as solar corona. Because if we don't know the exact physical, or if we don't give the physical values to the computer, so it will solve the equation in the same manner. But once we are doing on like dimensionless unit, we know that what are the normalization factors. For example, if we look at the scaling like this, then the length is 10 to the power 9 centimeters, so that's 10 megameter, and then temperature is 10 to the power 6 Kelvin, which is 1 megakelvin, and then there is density 2.34. Depending on these three sets of primary variables, the other variables will be solved by this equation. Now this technique is only for solar corona. Now let's say you want to go to a region where your density, temperature, length, these things are different. Okay. So we have equations which are going to solve in solar corona. So due to that, what we do is we just divide each sets of this, like rho will be divided by this, let's say rho star. Okay. So that will give you a rho bar or something like that. C will be like T by T star. That will give you like T bar. Okay. So this rho bar, T bar, those are dimensionless things. So that's what we are giving in the code. But for doing that, we are dividing the variables by certain things. Now this rho star, T star, everything, those things are what? Dimensionless, like normalization factors. Those normalization factor depends on in which plasma system you are going to solve those equations. So these are the values for this. Let's say rho star, here this rho is nothing but this rho star. Okay. Similar T star is nothing but this T. So these are sets of normalization factors while we are solving the equations in solar corona. Now what if we want to use the similar sets of equations in the let's say some other term. For example, we want to go to a length scale which is in 10 centimeter. Okay. So initially we are in a length scale of 10 to the power 9 centimeter. Now we want to go up in a length scale which is 10 centimeter. Okay. So what happens is, if if you look at this R equals to A R1, for example, you have this RC, which is R means length. Okay, so RC means R at point. Okay, so you will have RC equals to A R and then L for let's say L laboratories, which is having a length scale of S. So here, from here, you know what you have. So you would have the conversion factor of A from this, right? What you need to do is 10 to the power 9 for R, A multiplied by 10. That would give you a 10 to the power 8 conversion factor. Similarly, for temperature, here the second thing is rho is density. So for corona, as you can see, so rho is defined as gram per centimeter. So that can be written in terms of number density also. That number density will be 10 to the power 9 centimeter. Okay. So let's say if we have number density Nc, so that is Nl. Because the other thing is what? Mass. You are going from mass density to charge density. Sorry, mass density to number density. Okay. So you are just dividing by something which is a constant quantity in both of them. So then Nc is first U into N. So what happens is, let's say Nc is 10 to the power 9 Cv minus 3, and then you want to go in a laboratory system where the number density is 10 to the power 10 centimeter. Rho R is like the constant and then T. Okay. So using this and using this P equals to Cp for corona and for let's say a plasma system which is in lab, if you know how the temperature is going to change, you could easily find out what should be the conversion factor C. Okay. Once you know that A, B and C, the other quantities should follow this equation. So these three equations are in your hand. How are you going to change the parameters A, B and C? But the other quantities should follow the equation, because those only depends on A to power B by C or to power C by B or to C. So you can't define those as other ways. This should follow those equations. Okay, that's how you can change the normalization factors from a certain plasma system to other plasma system, with which you are going to divide the physical variables to make the dimension.
Just to write the same, you use the equation for Rho that you use for total mass that you use for sun. So now it becomes right.
Yes. Because in sun you have the length scale, everything, the dynamics is happening over a megameter scale, and then in tokamak everything is happening at a centimeter scale. But do you want, if you want to solve say dynamics by the same type of equation, this is the way.
Everything is fine. So how do you evaluate this number density?
Number density.
Number density.
So you have 10 to the power 9 centimeter minus 3 in corona. So that is what we have as the number density. And then let's say we have a system. This is a like this number density is from magnetic reconnection equation.
So these are the numbers.
We know these numbers. This is how we are going to find out the conversion factor initially, because we know what should be the temperature in a system, what should be number density in that system, and the length scale over which the thing is achieved. If we know those things, we are going to solve for A, B and C. Once we have that, we have to have this equation in mind. We don't have the equations to give those things. So now we have
your equation are of this system. Of this equation you are of this system. Of transfer from corona to this system.
yeah. Let's say you are solving the equations in this length, and then you are going in this length. So you have to see how the normalization factors will change, because using that only you are making dimension. So that's how scalability will come. So then okay, now we have equations. We know how they can be made scale independent. Now we have adaptive mesh refinement. So most of the people what we do in simulation, we will have either 2D domain or let's say 3D domain, right? Depending on dimension and depending on how many parameters you are going to solve, your data size will increase. And once you have a very high data size, it's conversion or analyze the data properly. Right? So adaptive mesh refinement tells us that, okay, firstly, if you look at these simulations, what happens is we have a very higher scale of box, like 0 to 80 megameter in Y, and then in X, I have just plotted maybe minus 30 to plus 30, but this box is like minus 80 to plus 80. We have a very higher scale of domain, but the entire dynamics of whatever is happening, that's happening in this portion. Right? In other portions, you don't have anything in scaling in time. Okay? So what you want? You want very less size of data, but at the same time, you want to resolve all the dynamics that is happening in the system. Right? So therefore, you want to have very higher resolution where the dynamics is happening, but where there is no dynamics, you want to have the coarser resolution. So you are not losing any kind of physics or any kind of dynamics, but at the same time, you will have a very smaller data size. Okay? So that's where adaptive mesh refinement comes. So as you can see from this, we will have different boxes, right? So this is the same picture with some zone view. So this is a straight thing where everything is happening. So you can see here the box size are very small, but then here the boxes are much larger because nothing is happening in this portion. You are not going to have higher resolution here. We will have higher resolution only where the dynamics is happening. So this higher the dynamics is happening, so that's why we have very smaller box. That means higher resolution. Okay, that's how adaptive mesh refinement. So now how does it work? So as we go for iteration, so we will have a discretized blocks. So initially, let's say we have we can resolve this and this. So we can resolve this point and then this point. In between that, if anything is happening, okay. In between them, if anything is happening, we are not going to resolve it, right? But then, let's say some dynamics is happening in this lens. You want to resolve it, but then nothing is happening, you don't want to resolve it. What happens is, at each iteration scale, you would calculate second order derivative of the variables in which you want to see whether there is any change. If the second order derivative is much higher than user defined threshold, so then it would split that block into, let's say here you have one data point here and another is here. So then it splits it into blocks. Therefore, now you have one point here, and then one point here. You have got a higher resolution. Okay. So you want to solve second order derivative at each point. If it is higher than threshold, so then it would break that block into. If it is not, it will remain the same. Okay. So that's how adaptive mesh refinement works, and that's how we do the simulations with lower data size, but at the same time with resolution by reference. So okay. So since I have 5 minutes, so I just okay. Very specifically, so J cross B will have two terms. So this is the Lorentz force that we have in the momentum equation only because of presence of magnetic field. If you see from these two terms, so this is like V dot del B, which tells that if we have magnetic field which is changing along the magnetic field, then only this will be normal because V dot del B. So V dot del tells that along the magnetic field only you are changing, taking the del del X, del del Y, del del Z, and then the changing magnetic field is only along the magnetic field. That's only possible if you have curvature. If you have just straight field lines, there will be no this thing will be zero. So that's magnetic tension force, which just wants to diminish the curve and straighten the field lines. So if you have straight field lines, this will not be zero. And the second term is d square by 2 mu, which tells that gradient of d square by 2 mu. So if you have magnetic field strength somewhere higher, somewhere lesser, then only this will be non-zero. So you can see from this T. So here these are the magnetic field lines which are more more closely spaced. So therefore you have a higher magnetic pressure here or magnetic strength here and the lower magnetic strength here. So there will be a resultant force going in this direction. While in this case you would not have any kind of force. Okay. I think I can skip this and okay. So one specific case that we have is magnetic reconnection. Now here we know from our textbooks that two magnetic field lines would not touch each other or break each other. Right? That's one specific scenario in which two magnetic field lines can touch each other, can break each other, and then reconnect with different opposites. It only happens only if you have this term is higher than this term. Okay? Because due to time, I am not going to do this. So this is magnetic reconnection. Why it is important? It can happen in different plasma systems, and then it can produce heat. It can accelerate charged particles. It can eventually accelerate the plasma itself. So due to its occurrence in different plasma systems and due to the heat production and everything, it is very important process to start. Now, this is a very laboratory scale. This people has done some experiment. I am not expert of, I could not describe this big. Okay. So they give some currents or something, and then eventually they see that once we have del T, which means that once this current is going higher with time, so they see that this flux force, these are oppositely directed field lines, and they come closer. In between them, there will be higher current density. It will make a current shift. So you have positive, you have negative magnetic field. This is coming closer, so you have card of B that will be very higher. So that creates a magnetic field. So that creates a current shift. In between that, there will be a reconnection. And then eventually, if it goes down, so in that case, it will have a full reconnection. Okay? So you have current shift in this direction, and then you have current shift in horizontal direction. So we don't have experimental facilities, but we want to have a very easy scientific idea. So we start with the Biot-Savart law, let's say. So what we have is a finite tolerance. Here it is for infinite tolerance. This equation will be changed for finite tolerance. I am not showing the exact equation. So what we have is we have 4 current carrying wires. Like these are 4 current carrying wires, and then this will create this resultant magnetic field. In between that, there will be no magnetic field, which means this is the magnetic null region. Okay. So this could be taken as XY. This is the snapshot from the XY plane. In our simulation domain, what we have is we have only this one thing. So the current carrying wires are very much far away from the boundary, and within this wires, DC current is changing. So these field lines are not going to change if we don't give any other observation. Now we consider two more wires close to boundaries in which we are giving AC current. That means it is changing in time. Once we have that, what happens is del V is going to be non-zero, and therefore the counterbalancing act of these two terms will not be there. So what happens in terms of results is, you can see this is current, this is H component of velocity, this is density and temperature. So you can see at this point you will have a vertical current shift that we have in that experiment, and then within the current shift there is a higher temperature. So that's reconnection within the current shift, which basically liberates the magnetic energy and transforms it to the heating. Due to that heating, you have higher temperature increasing. Okay. At the later stage, once we change, because we have AC current, so we will change the direction of the AC current. So at the later stage, now the current field is forming in the horizontal region, in the same set of simulation. Now you see everything is happening in the centimeter scale and the time scale is microscale. Okay. Now we do the similar kind of thing in solar corona, so you can see here some pulse is going, and at this location we have a magnetic null point. So it interacts with it. It generates a current sheet which is horizontal in nature, and then within that we have some plasma blocks which are interacting with each other. Depending on that, the interaction that generates some little like electrons which are propagating in the upward direction. Okay. So now we want to know. So we have plasma which has density and temperature, but we want to know how does it look if we capture this dynamics by some spacecraft. So what we have in space is the solar dynamic observatory, in which we have atmospheric and telescope, which are different filters of different wavelengths, which captures solar dynamics at different wavelengths and temperature. So depending on these response functions for different filters, which has peak and at different temperatures. So we will use the density. We will use this GTEC. GTEC is nothing but this response function. Using both of these, we would find that how the intensity will be there at particular temperature for particular density. Okay. From simulation we have those components, but we want to know how the observables will look like if we capture them by spacecraft. So that's what we see for, let's say, AIA 171, AIA 211 and AIA 94. These filters are at different temperatures. 171 is 10 to the power 5.8 Kelvin, 211 is 10 to the power 6.3 Kelvin, and 94 is at 10 to the power 6.8 Kelvin. So those are different temperatures. So everything is from simulation here, but then this is where we see that how it should be look like in different temperature filters. I think
plasma, if we can take a few questions.
So, you could take the graph on the left for the small system. You put this ideas of like 4 wires, and then you put the alternating current. So, how does this actually appear in the solar or in the sun-like structure?
so. In sun, I am not talking about sun here.
Yes,
I am
yes,
talking about the laboratory setup.
But still, it gives like what
It can happen. Like,
sun.
for example, like in sun we consider some poles instead of coils. Okay. So like magnetic dipole. If you have a positive pole, you have a negative pole. Okay. So instead of having the poles which are very stationary at certain space, which is not moving with time, so those field lines are going to be same. But then if some like flows are there or some homogeneities are there, we should create more shearing or something within the field line that will create a AC current or something. That's how that's related.
You are showing one place like direction of magnetic field breaking and then it is forming in another direction.
Yes.
So what were its time scales?
What?
Means on which time scales it's happening?
Yeah. So mainly two field lines should not interact with each other. But then if you have, okay, so let's just we have these two terms. I don't know equals what happens is you go for the dimension analysis. You go for dimension analysis, so this is dV by L equals to eta V by L square, right? In dimension analysis, what happens is that P should be eta by L if these two terms should be same, right? But then if you have a V which is greater than eta by L, so what happens is V is your plasma inflow, and a plasma will take the magnetic field with itself. Okay, but then eta by L, what is the diffusion velocity with which the higher magnetic of magnetic field would be here. Okay, so this is your speed of diffusion with which the magnetic gradient should decay, right? And this is with which the plasma will flow along with the magnetic field. Now, if you have a plasma flow, is coming at a higher speed than the diffusion speed, then only these two fields which are oppositely directed, they can reconnect each other. This is a very specific case or specific physical condition within which under which this will happen. Otherwise, there will be
Any comments or suggestions for that?
Plasma contains so many large number of electrons and atoms, high temperature, so they have velocity. Then how they are sustaining this electric field and magnetic field? So they are moving randomly. So how you effective
so
magnetic
here most of the magnetic field that I am showing in this equation, the major contribution is coming from the external not in the motion of the okay. Let's say if this is 100 watts, that would be maybe 0.1 watts. This is much higher than that.
So the plasma is moving because of that external
Yes. That was very minimal contribution from the external because that's a microscopic fluctuation or anything. And that would be averaged over. Well, this is going for this.
What are the input parameter of this? Like this is between of this movement and
So let's say this is the equation, right? What we have? Density, we have velocity, we have pressure, we have magnetic. And this electric field is given as E plus B cross C. Electric field is a secondary quantity. It could be calculated as E equals to minus B cross B plus C. And then J is started. So what we have? We have rho, which is the independent parameter. We have velocity, which is the independent parameter, and then we have pressure, and then magnetic quantity. These are the states what we have to give initial condition and then boundary condition. Then everything will be
if there is any other question, we can discuss it later. Thanks for
attending the seminar. Actually, it's a very difficult task for me because I never give this kind of seminar because every time it's very specific to the field in which we are working. I prepared this for this seminar only. This is nothing to do with my work. Most of the slides are only prepared for